There, it started. Okay, so this is on the practice teacher exams. So this one's easier than the, I don't say this in any demeaning way, just that it's a different type of test than the GRE thing. So we have this situation here. Let's see. I'm just going to draw this. This is y degrees. We have A and C and B. And it says that the measure of arc ABC is 3 pi over 2. Okay, so that's this right here. I believe that's the way that you're supposed to interpret that. Arc ABC is 3 pi over 2. And we're supposed to come up with y. The y, oh, in degrees, of course. So there's this rule that you might have remembered from geometry class, but if you didn't, here it is. And that is that whenever you have an angle like this that touches the opposite side of, what's it called, like a circle like this, that the measure of this, the measure of that angle, or that arc, is double the measure of this angle here. So that's the rule. And I'm sure Dr. Brad could prove that to you. I don't know if you haven't done anything like that in geometry class, just out of curiosity. I'm sure that it's coming, but that's something that can be proved. Don't put me on the spot and make me do it right now, but I'm sure I could figure it out. So anyway, with that said, you can figure this out now. This is going to be pi over 4, which is going to be a 45-degree angle there. Oh, I did not bring the answer key. Darn, I should have brought the answer key because, then I could have just told you what the answers were and you could know whether you got them right or wrong. I apologize. I was so focused on grabbing this and grabbing this that I forgot the book. So, but anyway, there it is. So a little geometry knowledge there.
If the point was in the center, would it just be the same?
So yeah, if you mean the vertex of that angle, if that vertex was the center of the circle, yes, it would just be pi over 2. So that's the rule about circles like this. If that's the center, then the angle is the same as the measure of this arc. Those are the same. All right, anything else about this front or back page? And then I've got a question for some of you, not all of you, just some of you, because I'm curious about something. But all right, front and back, it seems okay? All right, that's all right. Number 9. Yeah, let's take a look at 9 then. Yeah, that's fine. Number 9. Okay. So arithmetic. I guess this is dealing with this word arithmetic. Arithmetic sequence. And this is probably more than you wanted, but too late now. Whoops, that's a Q. Geometric sequence. So this deals with this these words. The first one. This is common difference. Is the definition of an arithmetic sequence. So pick a number, any number like 7, and then pick another number like 3. Just add 3 to 7 continually, and you have an arithmetic sequence. So 7, 10, 13. 16, 19, etc. That's what arithmetic means. Geometric is the common ratio. That's the one that's more common actually in mathematics, at least on our level. You have a common ratio with the geometric sequence. So this would be something like this, 1, 4, 7, 10, etc. And then geometric would be something like this, 3, 6, 12. So you're multiplying by the same thing each time. So you get the picture. So getting back to now that I've got that out of the way, it says the sum of the first 50 terms of an arithmetic sequence is 100 and the common difference is 2. We want to know what the first term is. Well, first of all, we need to know what is the sum of an arithmetic sequence. So the sum is actually quite simple. The sum is always going to be the first plus the last. Whoa, whoa, whoa. Oh no, do I know this? It's the average of the first and the, okay, times the number. I think that's it. Let me double check. Okay, sorry. So we'll double check with this. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. Okay, so that's easy. We could verify this one. So let's do the first plus the last divided by 2 times the number of numbers. And so that's going to be 11 halves. That's 55. Is that indeed the sum of these? Let's check. 10, 15, 21, 28. You would think I would know this. 36, 45, 55. Yeah, okay. Yeah, I've got the right formula. So there's the formula for the sum of an arithmetic sequence. And so now we just have to work this out using a little bit of algebra. So it says that there are 50 terms. So the number of terms here is 50. We don't know what the first and the last are, but we can do this, that, let's see, a sub n is always the first plus n times the common difference. So the d there is supposed to be the common difference, and I know I'm kind of free-forming this, but this is the way it is here. Okay, so that's what I would use for the formula, and so then I could take this and I could say, okay, I want it the first term, whatever that is, plus the first term, plus the number of terms. Well, it'll be 49 because I'm doing 49 steps to get to the 50th term. So 49 times the common difference all over 2 times the number of numbers. Okay, we're almost there. And it says the common difference is 2, so we can put that in there. So you have 2 times the first number plus 49 times 2 is 98 divided by 2. You know what? I could have done this so much easier, but I'm just doing it on my, off the cuff here. I should have done it this way. Let's let a sub 0 equal the first term. And then that means that a sub 49, sorry, a sub 49 is going to be the first term plus, well, 98, because you're adding 2 to get each of the next terms. So I could have done that. Then this would be 2 times a sub 0. But regardless, we know that the total is 100. And now it's just a little bit of arithmetic, or algebra rather. So let's see, we divide by 50, multiply by 2. So 2 times the first plus 98 is equal to 4. Is that what we're getting? And that means 2 times the first is equal to negative 94. And that means the first term should be negative 47. I sure hope there's, good. There is a negative 47 there. I always, by the way, I think I mentioned this when we were doing the GRE problems, that a great strategy for doing multiple choice when it's math is to cover up the answers, do it, and then if you get an answer that's on the list, it's probably right. You might get lucky, but it's probably right. There's probably actually, now that I see the answers, another strategy with this is to just do try it with each one of these numbers. So 47, common difference is 2, you'd have 47, 49, 51, and so on. If you add up all those numbers, for sure you're going to get way bigger than 100. Same with 48, way bigger than 100. So the only two that it's possible for is negative 48 and negative 47. So already you've narrowed it down to just those two, and then you could just guess, I suppose. But yeah.
Can you explain how you got a sub 49 equals first plus 98?
Yeah.
You explained it,
Yeah. So let's do a sub 0 is whatever it is, and then a sub 1 is going to be 2 times is a sub 0 plus 2. So whatever a sub 0 is, you get 2. So then a sub 2 is a sub 0 plus 2, which is a sub 0 plus 2 times 2. A sub 3 is a sub 0 plus 3 times 2. A sub 4, you see the pattern now, I'm sure, but let me just do that. And then, so a sub 49 is a sub 0 plus 49 times 2. So you're just adding 2 each time. Yeah, if it was geometric, there's another formula for geometric, but thankfully it's not, didn't ask for that, did it? Yeah, here here's the geometric, by the way. First, the first term, whatever the first term is with the geometric, and then you multiply that by 1 minus the ratio to the n plus 1, and divide that by 1 minus the ratio. So that's the, wait, is that right? Hold on a sec. I think it's not plus 1. I think it's just n. Yeah, that looks better. Yeah, so there's the, that's the geometric. So this is if you have something like this over here, where you're adding up everything there. Just take the first number, and then that 1 minus the common ratio to the nth power over 1 minus the common ratio. That'll give you the total, amazingly. All right, yeah, we can take our time and do whatever you want. This is all about you. I do have I have some project I want to do today that's based on what we did last time, but is there anything else that we need to look at? Take your time. Turn this off. Excellent. All right, well, if not, hopefully you wrote that up on something. I can collect it and say that you did it. By the way, I was thinking about this on the way over, that I've been done a poor job of maintaining the grade book in this particular class. And the reason for that is because I think everyone's doing a good job. I don't think anyone's flunking, and I think probably everyone's got an A average right now. You did great on the first test, and you know, you've been keeping up with things. So I have no complaints. There's one class that I have, I should tell you about, that the guy sits right back there, couple rows back there, and like he's always got he's like asleep or something, and then when I call on him, he like wakes up and he looks around like, what's happening? And then he like obviously isn't following. None of you are doing that. You're all with it, so you're good. I'll have the grade book updated for sure by the time midterms hit, because I'm required to submit midterm grades. But if you're worried about your grade, don't be. Don't be worried about your grade in here. So it's kind of perfunctory right now because you're all seniors and you're all doing a great job. Okay, let's move on though. I have a little project for us to do. So here is the project. So you remember last time we started taking a look at apportionment. And apportionment is just what to do when you have to divide a bunch of indivisible items in some way that makes sense, that is proportionate. Yeah, I'll get those homeworks in just a bit. But if we have, for example, these pencils. These pencils, and I'm giving these out as prizes to you guys based on how well you did on the last test. Now, almost everyone got 100 on the last test, but so I might be like, okay, anyone with 100 gets 2 pencils, and then if you didn't get 100, you get 1, but is that really proportional to how you did? So we want to do this because you can't, I mean, I could break a pencil in half and say, okay, you get half and you get half, but that's no good. We don't want to do that. It kind of ruins the pencil. So same thing is true with seats in the House of Representatives, or if you have a couple of, just as other examples of things that get apportioned, you would have things like buses. If you have a large metropolitan area and you're trying to decide where to put the buses, you want to put the buses on the lines that have the most riders, right? So if you have a particular route that has lots of riders, that would have more buses than a route with fewer riders. Now, I know we don't live in an urban area, but some of you might end up living in an urban area. I lived in Philadelphia for a number of years and rode the buses, and you know, I was thankful that they had buses where I needed them. So you would want to put buses where there are more people. But of course, buses, you can't cut them in half. You have to have a bus here or there, not half a bus there and half a bus there. I suppose you might say, well, we could have the short bus. but they don't make short metropolitan buses. Okay, so what I have here, another example, sorry, is when hospitals. Hospitals do this all the time. They apportion or allocate resources like nurses based on which departments have the most need. So if the emergency room has way more people in it than, say, the orthopedic whatever floor, then you're going to have more nurses in the emergency room than on the orthopedic floor. So you put the people where they're needed. So as an example for today, I have this fictitious university, or maybe this is a school inside of a university with 4 departments. You have the biology department, the computer science department, the math department, and the physical science department. So you have those 4 departments. You might say, why is there no engineering department? And it's because I made this particular problem up way, way back when we didn't have engineering here at MVNU. So that's how old this chart is, but the chart still works. Now draw a line. I should have bold-faced this line right here. So on the top, I know I've given you a page with 6 of these because we're going to do this several times. But draw a line underneath the physical sciences just to indicate that that's where the data goes away and we start having totals. So just to explain what I have here, I have the number of students or majors, so majors meaning like students, so there are 50 students at this university majoring in biology, 81 majoring in computer science, 124 majoring in math, and then 20 in physical science. Maybe this is somewhere like Rose-Hulman that focuses on math and science, I don't know. But there's my numbers. Here I have the total, so that 275, that's just the total of all of these. That's all that is. You could have done that yourselves with your calculator. Now here's the situation. We've decided as a school, limited resources, right? We can only have 18 faculty members, but we want to put those faculty members where they're going to be most useful. So we are going to apportion, what we've decided is to apportion those 18 faculty members to these 4 departments based on the number of majors. So in other words, math has, let's see, no, that's not a good example. Computer science has roughly 4 times as many students as physical science, and so you would expect computer science to have 4 times as many faculty members as physical science. Makes sense. Now, last time you had a couple of different ways of doing this, and we're going to actually, I named them, but what I want to do is I want to just formalize this, the ways that we're going to do this. Now, I got to confess that I gave my book away. I don't have the book anymore, but I've got one on order. So I've got a book on order. It's coming. And the reason why I gave it away is because I discovered that, unbeknownst to me, this book has a newer edition that is has a different name. That's the problem. Is I was looking for this book, like back in the spring, and had I known that there was a newer edition with a different name, I would have definitely just said, you guys get that one. But instead, you get the 1997 version, which is super old. I'm sure the newer one has updated data and so forth, but it's all the same content. Anyway, I'm waiting for that to come. So I'm really not sure exactly what your book says, because I haven't looked at it in a little bit. So I don't know what the next chapter is, but I assume it's something about apportionment, something about Hamilton's method. So what we're going to do today is we're going to go over Hamilton's method, practice Hamilton's method, and then we're going to go over Jefferson's method. So we have those 2. That's it. That's it today. We have another 35 minutes to do that. So let's do Hamilton's method. Hamilton's method is pretty straightforward. I think I mentioned this, the history of this, is that Hamilton's method was the one that was first adopted by the Continental Congress back in 1791. 1791, they said, this looks good, let's use it, it's simple. That's one of the nice things about Hamilton's method, it's easy. And it doesn't require lots of calculations, so let's use this, and sent it on to Washington, and Washington says, I don't think so. Veto. First veto. I think it's incredible that the very first veto ever used in the United States was for a bill that described a mathematical algorithm. That's basically what we're talking about here. But despite the fact that it was vetoed, we're going to look it over because it was used in let me think, I've got it in a PowerPoint somewhere, 1820, I want to say. So every 10 years, here's what happens. Every 10 years, we have a census, and then every 10 years, Congress has to decide how we're going to apportion the House of Representatives based on that census. And I think the first time Hamilton was used, it was either 1810 or 1820. But I've got that data. I've looked at the congressional record, let's just say, and it is, I have way more sympathy for my colleagues in the history department now that I've actually done historical research myself. Because looking at primary sources like the congressional record is really rough. It's so much nicer to look at a modern book where they've modernized the language and maybe, like the spelling is normal. Okay, so here's how we do Hamilton's method. Hamilton said, you know what we're going to do? We're going to figure out what the average district size is going to be. So average district size. So size. And we're using this language of district size in terms of, all I need is a cheap calculator, in terms of House of Representatives, but you can translate this to any application that you have. For example, if you're interested in bus lines, you would say average number of riders per bus. That's what that would be. Or if it was the nurse situation, average number of nurses per department. That's what that would represent. Whoa. Sorry. No, the nurse thing is not average number of nurses per department. It's average number of patients per nurse. That's it. Sorry, I had to think through what are we apportioning. So it just depends on what you're apportioning and how you're going to apportion it. Here we're apportioning representatives to districts. So average district size is going to be the number, so this is the total population divided by number of seats. And this, once again, is in the language of the House of Representatives. And it's not, it doesn't really make sense in terms of faculty, but in terms of this problem, it's going to be the students. So this is students over faculty. So this is going to be 275 divided by 18. So think of this as being the average number of students per faculty member. It's a similar situation. You can think of it as the House of Representatives, each of our representatives has to deal with a certain number of people in the population. And by dealing with them, I mean that whenever you visit Washington, D.C., you can go to your congressperson's office and ask for things like, can I get tickets to the White House or something like that. They have swag like that you can go and request. At least they used to. I don't know, in the post 9/11 world that we live in, I'm sure that it's not quite as accessible as it used to be, but it's still kind of, they have to deal with you on some level. Okay, so I'm getting 15.278 for this thing. So that's the average number of students per faculty member. So that's the first thing that Hamilton said. He said, let's just work this out. And this, by the way, well, we'll get there in a minute. Next, the second thing that Hamilton said is, let's compute what we're going to call the quota. Quota for each of these departments, each of the states. And the quota is just going to be the number of majors, or the number of people in the state, divided by the average district size. So for example, I could do this, 50 divided by 15.278. I'm going to run out of room. It's okay, I'm going to do this. Here, I'm going to divide. I think that particular, this was not enough room for the quota. So I'm just going to divide. I don't need as much room over here for this stuff. So the quota is going to be, this first one is 50 divided by the divisor. So that's another word for this thing, this 15.278. We call that the divisor. And that is going to be, just a minute, 50 divided by 15.278. And this is 3.27. So I'm going to change colors to make sure that 3.27. Now we're going to do the same thing for the other three departments. And so you could do this, because I'm not the only one with a calculator. So why don't you go ahead and do that. Divide 81 divided by 15.278, and you'll get the quota for computer science. And do the same thing for the others. I'm having trouble with this calculator. Apparently, I should not have chosen the cheapest calculator. I'm sure I could get it to work, but just leave it here. Let you guys do the calculating. All right, so who did the 81? 81 divided by 15.278? Yeah, what do you got? 5 point what? 30. Is it 5.3 exactly, or does it have more digits? 5.30 over the next one. Okay. Yeah, the only reason I'm being a little picky is because the next step is going to require us to know, like, if I had rounded, for example, if I had rounded this would have been 3.3. So that's the only reason I'm being picky, is I just want to make sure that I know exactly which one is bigger in, yeah, we'll get to it. This Hamilton did something that some of you did last time. And so let's do math. Math, who did math? Did you guys do math over here? 124, what did you get? 8.12, excellent, thank you. And then physical science, sad, little tiny physical science, what was that? 1.31, wow, so close. So that was, yeah, it's important to know which one of those is bigger, because the next step, so Hamilton says, let's compute the quota. Quota, if you think about what that word means, it's kind of like, this is what you deserve. Quota, this is what we deserve. So biology deserves 3.27. Computer science deserves 5.3. Now they're not going to get 5.3, but that's what they deserve. If we could divide up perfectly, the number of faculty, and math deserves 8.12. Okay, so that's the second step. I guess the first step is to compute what's called the divisor, or the average district size. Then we get the quota. Then the next step is to round down. I know, it sounds familiar, doesn't it? So I'm always excited when students come up with exactly the same thing. I mean, you gotta have some sympathy for these people back in 1790, and they're realizing that they have created this monster math problem, and they're just doing the best they can. So you got Alexander Hamilton, you have Jefferson, Webster was working on it, John Adams was working on it. We'll talk about their methods as well. But there's various methods that they came up with to solve this. And some of them are more simplistic than others. So 3, 5, 8, and 1. So we round everyone down. And then I'm just going to add that up. What is the total that we get? 3 plus 5 plus 1 plus 8 is 17. So the total is 17. So now I have to give out the extras. So the extras, and this is sort of similar to the way that you were thinking last time. The extras are going to go to, so here's what Hamilton said. So just so you know, I know that you had different ways of dealing with the extras. So we have one extra here, because we need 18 faculty, we have 17. So who gets the extra faculty? In Hamilton's method, who gets the extra one is going to be physical science, because physical science has the largest, is the closest, let's say, to, I know they're not very much closer than computer science, but they're the closest to the next one. So like here, you're closest to rounding up, let's just say. So that's it. That's Hamilton's method. +1 goes here, and then the final apportionment looks like this, and that is the answer for this particular problem, is those 4 numbers. I should have had another example of this on here. Let me just pull up another example of Hamilton's method just to do one practice. Sorry, I've got it here somewhere. Give me a sec. Wait. Okay, I'll just take a minute to, is this, yeah, this is it, good. Maybe? No, that's the same thing that we just did. That's the same thing we just did. Oops. My computer is not, why do I not have any examples? Hold on a sec. How about here? Oh, this one's good. Okay, this one's good. Yeah, let's do this one, because we'll be using this one as an example next week at some point. So here's the situation. So this is a House of Representatives. We have Algebrithia. So this is the country that has 3 states. So just 3 states. We have Algebrithia, Geometrina, and Trigshire are the 3 states. And for whatever reason, they've decided that for 3 states, they need to have 176 people in their House of Representatives. I know, ridiculously large, but there's a reason why I chose that number, especially since the population is only 176 or 17,600. So not many people in this particular thing. If it makes you feel better, you could always imagine that this is, these are thousands of people. So this would be 17,600,000 maybe. So then 176 would make a little bit more sense. But go ahead and see if you can compute Hamilton's method for this. So I've got the total here, I've got the number, this is the number, this is our target number in the House of Representatives, because it's not really stated here. So you're going to want to compute the, well, the divisor is first, but I think you could all do the divisor in your head, and then do the quota. And we'll talk about these in a minute. Those are important terms, but let's just do Hamilton's method with this. And I'm just going to copy this to my iPad here. So go ahead and see if you can do that. See if you understand the Hamilton method. Okay, I've got it copied over. So if you haven't copied it down, don't worry, because this is the same, it's the same numbers, but I've just got what we care about right now. So we're going to want to compute the divisor, and let's put a little line there, and then the quotas. Quota, wave around down. All right, now the divisor, I know that was a hard one, but what was the divisor for this one? Just 100? Oh yeah, it is just 100, isn't it? Yeah, divisor is just a, whoops, if only I could write correctly. 176, or 17,600 divided by 176. Yeah, just 100. Oh, so you could probably, I shouldn't ask. I was going to ask if anyone used their calculators, but yeah, you don't even need your calculator, I hope, for the quotas, do you? So let's just double check though. So we'll just go over here. And Rostin, what was the quota for Algebrithia?
92.3.
Yeah, you just divide by 100, right? Evan, what about the quota for Geometrina?
82.3.
Yeah, very nice. 3-1. And Sydney, what about Triggshire?
1.39.
Okay, yeah, that wasn't too bad, was it? You're just dividing by 100? Okay, now we're going to round everyone down, right? So we got 92, 82, and 1. Everyone's happy. So that makes 107. Oh, we're not happy yet. Because the total is only 175, and we need 176 seats for the House of Representatives. And so we need to give one more seat to someone. But Jaron, who do you want to give that last seat to? Triggshire, because, yeah, they have the largest. So you're just focused on this business down here, here, and here. And the biggest one is Triggshire. So we'll do the +1 there. And the final apportionment looks like this. Very nice. Ah, yes. I should say that this is so simple. This is super simple. And yet we don't do this. Not now. I think the last time we did it this way was in 1910, the 1910 census. Like I said, I've got the timeline. I'll show you at some point. But it's been a long time, over 100 years, since we've used this method, because there are problems, as you might guess. Anytime you have voting, or you're going to have problems. So we're going to find those problems. But let's go back to this page here, because we want to contrast this with Jefferson's method. So you remember I mentioned Jefferson's method was the one that actually got adopted in 1792 after Hamilton got vetoed. And so let's see what is Jefferson's method. So this up here, let me just label this. This is Hamilton. Let's see, I don't know if I should go down or over. I guess I could just go down. Yeah, let's just go down. Yeah, it doesn't matter. It doesn't matter. Okay, so, you know what I should have done? I should have put the Hamilton in here. There. That's good. So there's Hamilton. This one is Jefferson. Down here, we'll just put it here. You can put it wherever you want. It really doesn't matter. Let me just think for a minute. We have, I think I might have just the right number here. So you have Hamilton, Jefferson, Webster, Adams, Lowndes, and Hill Huntington. Now I got 6. All right, hang on to this. So eventually we'll have it all filled in with all the different methods. So let's try Jefferson, though. Jefferson's method. This is the first of what's called the divisor methods. So someone here came, I forget which group, but one of your groups came up with this method on Tuesday, which was beautiful. I was so excited, I got to tell you, when whoever it was said that this is what you did. So this is called a divisor method. And the way that a divisor method works is you don't mess, so here, we get the divisor, first of all. This is, so 15.278. So this is sometimes called the standard divisor, So up here, this divisor is the standard divisor, is the one that you're using. So with divisor methods, what you do is you modify the divisor. So up here, and here I regret not having enough, there we go. I'll just put another line there. I'll put modified divisor here. So what you do with a divisor method is you pick a modified divisor, and then you do the same thing whatever it is, whatever rule you use. And my memory from last time was that some of you said that what you should do is you should just round everyone down and that be done, right? I think that's the way you said it. And so here's how this would work, is if we use the divisor 15.278, then what's going to happen is you'll get those quotas up here. Sorry, I know those are the standard quotas. Well, it may be too late now. I was going to suggest you don't write this down. I'm just doing this as an example. 5.30, 8, because they're right above, so there's no need to. 3.1, I suppose I should put this line here. Give me a sec. The line right underneath physical science to indicate that that's kind of where we're heading. Okay, so the rule with Jefferson is you round down. So divisor method and the rounding method is round down. Now, just to give you a quick preview, Jefferson said, round everyone down, and that way everyone can be happy. John Adams said, round everyone up, and then everyone will be happy. Webster said, no, round everyone in the normal way, like you cut it off at 0.5. And then there was one other divisor method called the Hill-Huntington method. That one, you round everyone using this crazy method called the geometric mean. We'll go down later. So anyway, there's these various ways. So the only difference between the divisor methods, so Jefferson, round down. Adams, round up. The only difference is how you round. So we're rounding everyone down. So round everyone down. 3, 5, 8, 1, and then see if you've done your job. We have not done our job because we have only apportioned 17. So whenever that happens, we try again. So this is why I should have told you not to write all that down, because I'm about to erase it all. So sorry, because it's a repeat of what's up here. So that's the only reason I realized. So if you've written it, my apologies. But let me erase that just to show you now. Last time, you said, okay, we need to change the divisor, so we're going to pick another divisor. So instead of using 15.278, let's try, how about 14.5? Let's just try that. Now there's some rules or hints to help you figure out what to use for a divisor. Now I'll get a real calculator. And as I showed you last time, using a spreadsheet makes this way quicker. So doing this by hand is really a pain. So spreadsheet is really nice. So there's a modified divisor is 14.5. And now all I'm doing is I'm doing 50 divided by 14.5. And I get 3.4. And then 50, sorry, not 50 now, it's 81 divided by 14.5. And I got 5.6. And then 124 divided by 14.5, and I got 8.5, or 8.6. It really doesn't matter because I'm about to round down. And then the last one is 20 divided by 14.5. Got 1.4. Now I round, everyone goes down. Everyone goes down. 14, 3, 5, 8. Oh, I shouldn't have done that, sorry. Okay. 14, 3, or 3, 5, 8, and 1. And then check to see, did we do our job? 3 plus 5 plus 8 plus 1, oh, it's 17. Darn. Okay, so I think we could speed this up, though, despite the fact that we're doing it on paper and not on a spreadsheet. One way we could speed this up is to recognize that we don't care about the decimal. We don't care. It doesn't matter if this is 0.4, 0.9, 0.1. All that matters is the 3. So when I do this here and here, I'm not going to even bother writing down the decimal. I'm just going to round it down before writing it down. Another thing to help us out is a little rule of thumb, and that is that since this is a divisor, you're dividing everything by this. If you make this number smaller, it'll make the ratios that you get bigger. So the smaller this divisor is, so you'll make these numbers bigger. So what you're going to want to do is, if you undershoot, like here, I have too few seats, then make this even smaller. I know it feels kind of counterintuitive, but it's because you're using this as a divisor. So here's my new modified divisor. Let's try 14 and do the same thing. So let's see, I'm pretty sure that this is still going to be 1. Let me do 50 divided by, so here I'll just tell you what I see. I see 3.57. I'm just going to write 3. 81 divided by 14 is 5.78. I'm just going to write 5. 124 divided by 14 is 8.85. I'm just going to write 8. Oh, I still only have 17. I got to make this even smaller. So this could go on for a while. Anyway, let's try 13. I mean, I'm sick of this you could go to 13 and a half, but let's just go.
I would suggest 13.7.
Oh.
Must be.
Have you, did you find one that works? You did this one? Oh, you're amazing. Okay, well, okay. Here, let me flounder once. Sorry. I believe you. I totally believe you. In fact, I've done this so many times that I'm pretty sure I remember like 13.75, 13.7, somewhere in there works. But let me do 13 just for fun. You don't have to write this down because you know it's not going to work. You can do what Sarah said. So let's see, 13, and I got 3. And then I do 81 divided by 13, and I got 6, because it's 6.23, but it rounds down to 6. And then 124 divided by 13, and I got 9, and then this is 1. Oh no, I got too many. I knew it was going to be too many though. So yeah, so notice that I have too many, and because I'm doing a divisor, I make this bigger and it'll make everything smaller. So yeah, let's do 13.7 and see how that works. I'm going to guess that it's 3, 5, 9, and 1, but I'm going to double check though. I'm pretty sure the 3 is going to be 3. It's that 5 and that 9 that I don't know about. So it's correct? Okay, good. 13.7. Very nice. 9.05. So that pushed math just a little bit above, and then we get the 18 there. So that's the answer. By the way, there are other numbers that would work. So 13.7, not the only number that would work. I think 13.75 might work. I don't remember. But 13.7 is, there's a range of values that work. It feels like you're just floundering. And imagine doing this for the United States. 50 states. You definitely need a spreadsheet. But wait a minute, Jefferson did this. I know he only had like 16 or whatever it was then. But he must have done this with his 16 or 17 without a computer. So he's doing this. He probably actually had computers, but they were people. You know, back then, computer was a job. It really was back in the 1800s. People who did calculations were called computers. But anyway, getting back here. So yeah, the job got stolen by the computers of today. So there it is. There's Jefferson's method. So good. All right, let's see, what is it? 42. Do we want to do the next one? I don't know that we do. So Jefferson's method, we've done that. Hamilton's method. Yeah, let's just go back to this really quick here. Because as you can imagine, because we're dealing with mathematics intersecting with social things, you're going to find that there are going to be problems. And so just a little bit of language here real quick. And so the first thing is this idea of a lower quota and an upper quota. Let me put this up here. Just a minute, where's my chart? There it is. Okay, so lower and upper quota. So here's my thing here. And so the lower and upper quota are always going to be what's called the standard quota. The standard quota, you round it down to get the lower quota, and you round it up to get the upper quota. I'll explain what's special about these numbers in just a minute. So this would be 93, 83, and 2. So notice that I've just taken those and rounded them up to get the upper quotas and down to get the lower quotas. So it would make sense. Here again, we're using this fairness, and anytime you throw fairness into the mix, you know that there's a problem that's going to be coming next week, though. But it would make sense to always have, like, for example, Trigshire. Trigshire, no matter what method you use, you would expect Trigshire to either get 1 or 2 seats. You know, it doesn't make sense to go to 3 seats, does it? Why would you ever give Trigshire 3 seats? Same thing with Geometrina. Geometrina should always either get 82 or 83 seats. Never 81. It doesn't make sense. Why would you give Geometrina 81 seats? They deserve that many seats. Algebrithia, either 92 or 93. So that's the significance of the upper and lower quotas, is that that's sort of like a, you know, in one sense, that's a way of evaluating whether or not your apportionment is fair. Like if for example, Geometrina ended up with only 81 seats, you would think that they would have reason to complain. And I think with some, they have some leg to stand on there. Or if they got 84 seats, you would think that maybe one of the other states would say, wait a minute, it doesn't make sense. Why should they get more than 83? Okay, so that's what lower and upper quotas are. All right, I think that's all. So, like I said, I don't have a copy of the book, so I think that if you look, when you get done with the voting methods, you'll have to tell me what the next chapter is. But it would be good if we could move on. I suppose I could just pull up the table of contents here. Give me a sec. Probably should have done this. I'm hoping that my new version of the book comes soon. So let's see, is democracy fair? Table of contents. Table of contents. Okay, so what is the next? I don't know, why is it not coming? Yeah, you'll have to, maybe someone could loan me just for a sec. Let me peek. Does anyone have their book? You have it, wonderful. Let me just take a peek. Just want to remember, I looked at it at one point. Let me just see what the next section is, so we know we're done with this voting, we're done with voting, we're done. Apportionment, here we go. Oh, this is beautiful. And there's Hamilton. Okay, yes, let us do Hamilton. Hamilton, is Jefferson next? Ooh, Jefferson. Yes, no, we'll do both of them. Yeah, Hamilton and Jefferson. You can skip the introduction because we've done the introduction. So Hamilton and Jefferson, let me see, this is 10 and 11, activity 10 and 11. That'd be great. I'll put it up on the screen here. Thank you so much. So do it, the various calculations there. So this is, so 10 and 11. So this is the apportionment stuff. Apportionment activities 10 and 11. We'll save, I know you're chomping at the bit, but just to give you sort of a preview, this practice test, next Thursday is the conference that everyone's going to sign up for now, right? So do sign up for the conference. But eventually we will want to finish up the rest of what I gave you. So maybe you could hear, let's just do, how about page 2? Apportionment activity and then page, I know it's a lot of stuff, but the page 2 of the teacher test, example teacher test. So page 2 plus those 2. I know it seems like a lot, but you've got an extra, what is it, 5 days between now and next Tuesday? All right, I think that's enough. Let me know if you want to chat. I hope you have a wonderful day. There it is.